I think I can guess why most of you are in this talk today. It's because you've been to a lot of other talks this week that have been very practical. You've learned things that you can apply to your job as soon as you get back to work on Monday. Maybe you went to a really excellent talk on web accessibility and you're ready to go. But you've been overloaded with so much useful information. Now you're ready for a change of pace and you just want something that's kind of mind-bending. And you're in the right place for that. So I'm Mark Volkman. I'm going to tell you about Lambda Calculus, which was invented in 1936 before computers existed. Amazing. Now this URL down at the bottom here, in case you can't read it, it's github.com/mvolkman/talks. And you'll find all my slides there, including for this talk. Now, some people, when they hear the term Lambda Calculus, they think, oh, this must have something to do with math, and I love math or I hate math, but it's not that at all. The word calculus just means a method or computation or calculation in a special notation, and we're going to see exactly that notation today, and we're going to do some computation using that notation. So a little about me. I'm a software engineer from the St. Louis area. I've been doing consulting for a long time, 45 years of experience. I've written a couple of books. I'm working on a book on web components right now. So what is Lambda Calculus? Well, it's describing concepts that are fundamental to functional programming. And the big pieces here are first-class functions. And I can pass a function into another function, and a function can return a function. We'll see many of those today. And then there's the concept of currying, where I take a function that accepts more than one argument, but I split it up into a sequence of functions that I call in sequence to achieve kind of the same effect. And the purpose of this is to study how functions interact with each other. The purpose is not really to do something useful, or especially not efficiently, as we're going to see, but it's still amazing and it's Turing complete. And so anything I can compute with Lambda Calculus, just not efficiently. And what is it missing? Well, there's a lot of things that are not present in Lambda Calculus. There's no concept of Boolean values like true and false. I don't know anything about numbers. I can't just write down 7. There's no such thing as the number 7 in Lambda Calculus. I don't have strings, and there's no built-in functions to operate on those things, even if they did exist. So this was invented by Elonzo Church, and I have a feeling that he was thinking, you know what? I am an expert in all things logic and mathematics. This is so easy for me. What I want to do is put some real constraints on this and make the problem harder. Kind of like if he were a football or a soccer player and he said, let's change the field and I want the goal to be 1 meter wide because it needs to be more challenging for me. And that's what we get with Lambda Calculus. So even though those things don't exist, what you could do instead is you could pick some functions that represent them. And we're going to see exactly what Elonzo Church chose for those coming up. So all you have are functions. The functions can only take one argument, which is another function, and they can return one thing, which is another function. You could kind of compare this to slide rules. As you know, you don't need to know how to use a slide rule. You've got calculators and they work just great. But still, it's fascinating to kind of study slide rules and understand how it uses logarithms to get the results. And that's the way Lambda Calculus is. You don't need to know this, but it's fascinating that it could even work. I'm going to skip past the history, but you might want to take a look at this slide later. It's kind of interesting. So many of you, I imagine, are familiar with JavaScript, but I don't want to assume that everybody is. And we're going to be using some arrow functions in JavaScript. And so I want to start off by making sure that you're comfortable with the syntax of functions in JavaScript. And so here's a very simple function that I can pass in 2 numbers, adds them together and puts them in the temporary variable result, and then I just return it. But of course, I could shorten this a bit, and I'll show you that in just a second, but here's an example of calling it. Very basic. I just pass in 2 numbers and I get a result back. But I could rewrite that function like this, no need for that intermediate variable. And in fact, because there's only one expression inside the function, I might as well shorten it even further. Now, instead of using the function keyword, I could use an arrow like this, and the body is the same as over there. And I could write it like this. Again, the body is the same, but here we get to something different. Because there's only one thing inside here, I don't need the return keyword and I don't need the curly braces. I can just write it like that. So we're leading up to this, that I could have a curried version of my add function where I pass in not two things, but only one thing. And what it returns me is another function that expects the second thing, and then that'll give me the result. And I can use it, well, I could also rewrite it like this. The same thing I did here, because I only have one expression, I can get rid of the return and the curly braces, and wow. We're going to see a lot of functions written like this coming up because this is very convenient for Lambda Calculus. So these do the same thing, and I could use it like this. I could call curried add and pass it 2, and I get back a new function that always just adds 2 to one other number, and then I could use it like that. But of course, I don't need this intermediate name add 2. I could just do this. I call curried add and I pass it 2, which returns a function, and then I pass 3 into that, and I get the same result. Okay, so now we're all on the same page of how the JavaScript syntax works for defining functions. Now, the next several slides here are very formal, and if I was teaching a formal class on Lambda Calculus, I'd have to show you all this. In the interest of time, I'm going to skip past most of these slides, but feel free to come back to this later and email me questions if you have any. But there are a few things that I really have to point out, and one of those is that in Lambda Calculus, you'll see a lot of variables that are just placeholders for some value, and we're not going to say what the value is, and it's always written as just a single letter. Then there's lambda abstraction, which is really just a fancy term for defining an anonymous function. And there is the official Lambda Calculus syntax, and then there's the syntax of all the other programming languages. And I'm going to try to show side by side here the difference between those syntaxes. So in Lambda Calculus, you write the Greek letter lambda, and then you have the parameter name, and then a dot, and it's followed by the body of the function. And if I was going to write the same thing in JavaScript using an arrow function, I'd have the parameter and an arrow and then the body of that function. So lambda abstraction is just defining an anonymous function, and no functions in Lambda Calculus have a name, so they're all anonymous. Now, if I want to evaluate a function that has a body like this, and remember everything in Lambda Calculus is a function, so A, B, C, X, they're all functions. So I'm passing in X, and then the result I'm returning is this body, and it would evaluate it like this. So pass B to A. Well, this is composing the two functions, and I get a new function, and then I pass in C, that gets composed, and I have another function, and finally I pass in X to that, and I get my final result. Now, often you'll see something written like this, which means it's a function that takes X, and it returns a new function that takes Y, and it returns a new function that takes Z, and then this is the result that I'm going to return from all of that. Now, I could write it like this, and that seems to imply that I could have a function in Lambda Calculus that takes 3 parameters. You can't really do that. This is just a shorthand notation that means the same thing as that. So it's always in the curried form. So now I've defined a function, and if I want to apply it, the way you do that in the Lambda Calculus syntax is that you have your function definition, which is what we saw up here, and then you just follow that with a space and all of the arguments that are going to be passed in one at a time. And I could do the same thing with JavaScript, and the main difference you see here is that arguments in JavaScript have to be surrounded by parentheses where they are not in the Lambda Calculus syntax. And so here I've got a function defined with Lambda Calculus, and I'm going to one at a time pass in the 3 arguments. And in JavaScript, I'd do it like this, where each one is in parentheses. All right, so we need to get into some real interesting parts of Lambda Calculus. And so I'm going to skip past all these formal pieces that you might find interesting to look at later, like what's the difference between a bound and a free variable? And what about all these evaluation rules? We've got alpha conversions and delta rules and beta reduction and eta conversions. Kind of interesting, but not necessary for all the examples that I'm going to show coming up. All right, so getting into the more interesting parts. As I said, there are no values like true and false in lambda calculus. So we have to choose a function that is going to represent those. And so for true, the function is what you see up here. And at this point, I think I'm going to start focusing a bit more on the JavaScript definitions. It's maybe a little easier to understand. And so here's a function. Now, while I have called these T and F, and you might think that they represent true and false, really you should think that they could be any value. So I have this function where I pass in a value, and then a second value goes into that. And the main thing to see here is no matter what the first two things are, I always return the first one. And that is the definition of true. A function where it sort of takes two things and you always get back the first one. And false is the opposite of that. It's like a function where I can give it two things, and no matter what I give it, I always get back the second one. And why are these good choices for representing true and false? Because it makes it really easy to implement functions like not and or. And that's what we're going to see now, is how could I use those in that way. Now, I want to be able to have code that I can actually run in JavaScript, like using Node or Bun or something. And so I have to put these function definitions into some name so that I can test them. And so in my code that I'll share with you later, these are my definitions. And notice that true has an underscore at the end. I can't just call it true because that's a keyword in JavaScript. And so I've got the underscore there. And so these are the definitions that I'll be using. And now we can start to do something useful. So I want a function where I can give it the function for true or the function for false, and it'll give me back the other one. And so here is that function, and assigned to this name not. And so B here represents one of those Boolean functions. And I'm going to pass in the function for false and then the function for true. And why does this give me the not? Well, just briefly stepping back into the Lambda Calculus syntax for this, it would look like this. I pass in some Boolean function, and then what I want to evaluate is that Boolean function passed false and true. Well, what if I pass in this function? Remember, this is the function that represents true. It takes two things and it always returns the first one. So if I'm evaluating this body, it means that I take this part underlined in blue and it becomes the value for B. And so I've rewritten that right here. And then here's the false and here's the true. But what's the value of this? Well, this function takes these two things, but no matter what I give it, it always gives me back the first one. So it will give me back false. So this worked. I gave it the function for true, and I got back the function for false. And the same thing happens here. I'm giving it the function for false. This part is the same, but this function for false always gives me the second thing. The second thing was true. And so the result when I give it false is true. And there I have it. I've got a way to define true and false, and I can get the not of one of those. Well, as you can imagine, we can just kind of continue with this, and I can write a function that can and these two together. So here is my and function, and I give it two things, and it's going to give it, I have to pass in two values to it. So the first thing that I give it is the y value, the second one, and then the second piece, I just say it's always false. So imagine that the first argument that I give it is false. I'm anding two things, and the first one is false. We already know the result is going to be false. It can't possibly be true if the first one was false. And so if x is the false function always returns the second thing. And so that's this. That worked. Well, what if the first argument was true? Well, in that case, the final result is whatever the second one was. If it was if it was true, the result is true. If it was false, the result is false. And so that's what I get. The true function always returns the first thing, and the first thing I gave it was the second one that I passed in. And so now I have a working AND function. OR is pretty similar to that. I say the first thing I'll give you is true, and then the second one is just whatever the second value was. And so if the first thing I gave it was true, I know I'm going to get back the first thing. True always gives me the first argument, and so it's true. If I'm ORing and true and false, it's true. If I OR true and true, it's true. Okay. If I begin with the false function, it always gives me back the second thing. And so I want it to be whatever the second one I passed in was. So ORing false and false gives me false. ORing false and true gives me true, the second one. Cool. So now we've got all the basic Boolean functions covered. This gets more interesting when we have to throw in numbers. So we have to come up with functions that represent the numbers. Now, we're not working with floating point here. In fact, we're not even working with negative numbers. We're just looking at 0, 1, 2, and so on. And so the way that Elonzo Church decided to represent numbers is to say, you give me any function and any value, and if that function is never called, that's 0. But if you call the function one time, passing it the value, and then you give me back the result, that's 1 because you called the function one time. And if you call the function, passing it the value, get that result, and then call the function on that again, that's 2. And it just continues on from there. And so you can see in this table here that, of course, this is the function for 3 because it called the function I passed in 3 times, beginning by passing it that arbitrary value that I gave it. So these are called Church numerals. And if that's the way that we're going to represent numbers, now I can start to do some interesting things, like write a function that can take 2 of those and add them together. So the first step in doing this is to be able to answer the question, what's the next number after a given number? Like if I say, what is the successor of 3? It's 4. So how could I write a function that does that for me? Well, when I apply a number function to some value, it's going to do it that many times. Because remember, that's what we saw. The definition for 3 is to call the function 3 times. All I need for the successor is to call it just one more time. And so if I ask, go over here to the JavaScript version, if I say, what is the successor of n? Well, I need to also give it some arbitrary function and some arbitrary value. And to call that n times, I just need to do this. N with the f and the x, it's going to call this function f n times. But then if I throw this f out here, I'll call it one more time. And that's it. And so now I have a function that can tell me what's the next number. And again, of course, it's not giving me a number. It's giving me back a function that represents that number. Okay, so what is the successor of 2? Well, here's 2. And if I call it one more time, that's the function for 3. So now armed with this, and by the way, I'm going to start pointing out the order of these functions because as you'll see as we go along, it gets worse and worse. Like we get up to n to the 4th order on these things. And as I said earlier, this is not about being efficient. It's about amazingly being able to do it at all. These are also called piano numbers. Piano numbers are defined as the number 0 plus every number you can get by calling the successor function repeatedly. And that's what we have now, a successor function. Okay. Another thing that we're going to need here is how to find the predecessor of a number. And this is amazingly complicated. In fact, Elonzo Church could not figure it out. And instead, one of his students figured it out for him, and he did it while he was sitting in a dentist chair. I guess he had nothing else to think about at the time, and he came up with a really interesting solution to this. And why is this a hard problem? Successor was so easy, we just needed to call the function one more time. But how do you call a function one less time? There's not an easy way to do that. And so here's the recipe that Stephen Klein came up with. He said, how about if we come up with a way to represent a pair of numbers like 0, 0? And then I say, the way I'm going to get the predecessor is I'm going to create some new pairs starting with this. And if you want to know what the predecessor of 4 is, then 4 times I'm going to generate a new one of these pairs. And the way that I generate a pair is I'll say the first number in the new pair is the same as the second number in the previous one, and its second number is going to be the successor of that. And so what does that really do? It looks like this. So if I want to know what is the predecessor of 5, I need to generate 5 new pairs starting with 0, 0. And so the first one, I take this 0 and I put it down here, and then I get the successor of that, which is 1. And then I take that 1 and I put it down there and I get its successor, and just keep going like that. And now I've got my 5th pair. And if I just take the first number out of that pair, magic, that is the predecessor of 5. And this works because I've introduced a delay in incrementing the first number. I didn't increment it, but then I do, and then that works. Amazing that he figured this out in a dentist chair. So how could we actually implement this? Well, we need to have some helper functions here. First of all, we need a way to represent a pair. And so this function says, you give me 2 things, plus give me some arbitrary function. And then what I'm going to return is the result of passing x to that function, and I get a new function, and then I'll pass y into that. That's what I've decided I'm going to use to represent a pair. And so if I have that, how could I ask the pair, hey, what is your first number? Well, p here represents one of my Boolean functions. It represents the pair. And then if I have my function for true here, well, true is the function that I'm passing in up here. And so it becomes this spot. And what does the true function do? It gives me the first thing. So it'll give me that x, which was the first part of my pair. And you do something similar for the second one. It's just that I pass in false instead. And so now false becomes the value of f right here. And it gives me the second one, which is y. So that's 3 of my utility functions that I need. And I need one more, and it's this one, this function that he called phi. This is giving me the next pair. And so this function says, you give me a pair, and I'll produce a new pair for you using that function. And the parts of that pair are the second number in the pair that you passed in, plus the successor of that second number that you passed in. And so this is our recipe for back on the previous slide where I was showing you all the new pairs being generated. And so now that I have this, I can write them like this in JavaScript, and I'm ready to go and make use of that phi function. And so now to put this all together, I need this. So this says, to get the predecessor of the number n, what you need to do is you need to start with the pair 0, 0, and you need to call the phi function on it n times, generating new pairs. And when you finally get to the last pair, you need to ask for the first number that was in that pair. And there we've got it. Now, there's a problem here. Remember I said earlier in Lambda Calculus, functions don't have names. And I've written a lot of functions that have names. So you can't really do it like this and be correct in Lambda Calculus. What you have to do instead is write some mess like this, which is like a combination of all those things that hardly anybody could be able to make sense of. It's the same thing, it's just combining all of the pieces. Now, an interesting thing I skipped over is what is the predecessor of 0? Well, the way I wrote the predecessor function, it turns out it's 0. And that's a fortunate thing. It makes it so I kind of don't go off the rails in some things that I need to do here. Okay, now this function is order n squared because the successor function, as we saw, was order n, and I'm going to call that n times. So if you want to know what is the predecessor of 100, yikes, there's a lot going on there, but it works. Okay, so now that we have successor and we've got predecessor, we can start to do some real work. I can write an add function, and so for adding two numbers together, this is sort of like iterated successors. If I want to know what is m plus n, well, I could just start with n, and I could call the successor function on that m times. So I start at n, and I just boom, 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 work my way up, and then I get to the result. And so here's what that would look like. I pass in two numbers, and I say apply the successor function m times to the value n. And as an example of this, here I want to add 3 and 2. So I need to 3 times apply the successor function to 2. And so that expands out to this, successor, successor, successor. And now I can start crunching it down. What's the successor of 2? It's 3. What's the successor of 3? It's 4. Successor of 4 is 5. And there we did it. We added 3 and 2. This is also order n squared because successor function is order n, and I'm calling it n times. As you might guess, subtraction is real similar to this. I'm just going to use the predecessor function instead. And so I pass in my two numbers, and I want to apply the predecessor function n times to m. And so we kind of switch the order of these things around. So if I want to know what is 5 minus 2, well, I need to apply the predecessor function 2 times onto 5. And so it expands out to 2 calls to predecessor. Predecessor of 5 is 4. Predecessor of 4 is 3. 5 minus 2 is 3. This one is order n squared because predecessor is n cubed. Predecessor is n squared, and I'm calling that n times. So pretty expensive to do subtraction. It works. Now another thing to notice here is what if I want to subtract 2 minus 5? Well, as I said, there's no negative numbers here. And as I said just a bit ago, predecessor of 0 is 0. And so that is going to give me 0, not a negative number. Multiplication is also similar. This is just iterated addition. If I want to multiply m and n, I can start with 0, and I'll call add n times, or add on to n, do that m times. Okay, and so here's what that code looks like. And as a worked example, if I want to multiply 4 and 3, then 4 times I need to add 3 to the 0. And so this expands out. 4 times I'm doing add 3. And then I can start crunching it down. 3 added with 0 is 3. 3 and 3 is 6. 3 and 6 is 9. 3 and 9 is 12. And we have multiplication. So the kind of pattern for addition and subtraction and multiplication are all very similar. I'm just making iterated usage of some other function that I've already defined. Now you might think the next thing I'm going to show you is division. Sadly not. Division is incredibly complicated. In fact, in Lambda Calculus, you need to use recursion to implement division, and we haven't learned how to do that yet. As you'll see coming up, that's complicated because when functions don't have names, how in the world can you call it recursively? So we'll see a solution to that coming up a bit later. So we'll skip division for now and move on to exponentiation, which turns out to be a lot like the ones we've already seen. It's just iterated multiplication. And so if I wanted to know what is m raised to the n power, I could just start with 1 and I could call multiply m on that and do that n times. And so this pattern is very similar to the previous ones that you saw. So if I want to know what is 2 to the 3rd power, then I just need to repeat multiplying by 2 3 times, starting with 1. And so this expands out to the 3 times that I'm going to multiply by 2, and then we crunch it down. 2 times 1 is 2, 2 times 2 is 4, 2 times 4 is 8. Got exponentiation solved. There's an alternate way that I could write this, which looks much simpler. If I just say I want to use the function n and I pass it m, it turns out that gives me the same result. And that's because, as we saw, the function for the numbers just repeats a thing a number of times. And so that turns out to be a much simpler way to write it. But writing it this way matches the pattern of the other ones we've seen. And doing it that way, you might think of it like this. Like, here's my number for 2, and then I want to replace all of these functions with doing that twice. And so this one gets 2 applications, and this one gets 2 applications, and so now I have 4 of them. And now if I replace all of these with 2 applications, then I end up with 8 of them, and I get the same result. I'm going to skip over function composition here because I want to get started in talking about recursion, because that's kind of the most interesting part and kind of a challenging part. And so one thing this requires is understanding the notion of a fixed point. Many functions have a fixed point, and that just means there is a value that I can pass to the function, and the result is the same as what I passed in. And so as an example of that, the square root function has a fixed point at 1. Square root of 1 is 1. And the cosine function, if I pass in this value, then approximately the value I get back is the same thing that I passed in. And you could kind of think of it like this graph here. If I have this line here that's going through all the points, and you could think of the x-axis as the value I passed in and the y-axis as the result I got back, if those are ever the same, that's a fixed point. Why do we care about this? Well, we care about it because lambda calculus functions actually have a fixed point too, and it looks like this. What in the world is going on here? I've got this function where I can pass in x, and what it returns to me is the result of passing that x value into itself. And what I'm going to pass into it is the same function. And remember, when you're evaluating a function, what you do is you take this argument, which is the value right here, and you substitute it in for each of these. But what would you get if you did that? It would look just like this. And then you would evaluate it again and again, and every time you would just get this. And so this just continues forever. Sounds a bit like recursion, right? Except for in recursion, you need some way to eventually stop, and we don't have one yet. This is called the omega combinator, and it's the key to how we're going to be able to implement recursion. Now, the sad thing about this is that it certainly doesn't do anything useful. It's just spinning forever. We need to introduce something to make it do something useful. And as I said, we need a way to stop at some point. And so for our purposes, we're going to want to know, is a number 0? And so we have to have a function that can determine that for us. And so this is what the function looks like. You give me some number, and I'm going to choose either this or this. Now, it turns out that the function for 0 is exactly the same as the function for false. Go back and look at those. It's the same function. And what does the function for false do? It always returns the second thing. And so if this number that I'm testing is 0, I want to return this, the second thing. Is 0, 0? True, it is. But what if it's not? Well, for any other number, what's going to happen is it's going to choose this piece, and let's say that it was 100. It's going to end up running this function 100 times. And every time it's going to say, the answer is false, the answer is false, the answer is false. And finally, when I get to the end, the answer is false. And that's right, 100 is not 0. So this is my incredibly inefficient way to find out if a number is 0. That's order n, not order 1 like you might hope. And we need this to implement recursion, just like we need that omega function. So now we're ready to go, and we want to make that omega function do something useful. And so now we see the y combinator, not the omega combinator, but the y combinator that is built on top of it. And this part here looks very similar to what I showed you about the omega combinator. The difference is that we've dropped in this f. And think of the f as work that we want to do on each spin through this. So now it's going to do something useful for us. So expanding this out in its JavaScript form, it would look like this. So now I have a way that I can loop through this forever if I want and do some useful work. But what is the work? So we'll have to define a function to say what it is that we want to do. And by the way, this was invented by Haskell Curry. So let's apply this to computing the factorial of a number. That's a thing that we often do with recursion. So if I want to know what is the factorial of 4, remember that's 4 times 3 times 2 times 1. And then I'm going to stop because I'm going to reach 0. And in the recursive definition, you could say the factorial of 4 is 4 times whatever the factorial of 3 is. The factorial of 3 is 3 times whatever the factorial of 2 is. And so that's the pattern that we want to try to implement here. And so I need this function that I'm calling facgen, and that's going to be my f function in the y combinator that we saw on the previous slide. And so I'm going to pass in some function and a number, and I want to know what is the factorial of n. And so first thing I'm going to do is I'm going to check and see if that n is 0, because what is the factorial of 0? Well, it's defined to be 1. And so this function is going to give me back the function for either true or false. If it gives me back true because I passed in 0, then it's going to choose this function, which always returns 1. That's good. If I have 0, I want the result to be 1. But if it's not, it's going to return this function, which is going to do some work for me. And remember I said the factorial of 4 is 4 times the factorial of 3. Well, this is multiplying whatever that number was by the factorial of the predecessor of n. So if that's 4, predecessor of n is 3, I'll compute that factorial, and then I'll multiply by the n. Now, these are just functions, but they're not calls to the functions. They're just function definitions. And so this little bit right here says, call the function that I selected. So I have this test, and I'm going to pick either this function or this function, and whichever one I picked, I'm going to execute it. Now, this y right here, that's the y combinator function that we saw in the previous slide. And then we're just passing in our factgen function right there. And so this is the way it would work. I would ask for the factorial of 3. 3 is not 0, and so I end up over here. And so I'm going to multiply 3 by the factorial of the predecessor of 3, which of course is 2. And so I'm going to multiply 2 by the factorial of the predecessor of 2, which is 1 times the factorial of the predecessor of 1, which is factorial of 0. Factorial of 0 is 1. And so now we start crunching it down. Multiply 1 by 1 is 1. 2 times 1 is 2. 3 times 2 is 6. And there I've got it, the factorial of 3. So that y combinator is a magical thing. Technically, though, I sort of lied to you. This is not really the y combinator. It's the z combinator. What's the difference? Well, the difference is that the y combinator assumes that you're using a lazily evaluated language. There aren't very many of them, but Haskell is one example of that. In Haskell, when you have a call to a function, it doesn't really evaluate it. It waits for you to ask for the result. But JavaScript and most other languages are not like that. And that's why I needed this little bit here. And that's what makes this actually a use of the z combinator and not the y combinator. And so that's what this part is discussing. Well, now that I know how to compute factorials, I could apply the same approach to division. In division, I just need to keep subtracting a value away and see how many times can I subtract it, and that's going to be my result. But there's some difficulty here. I can't divide 7 by 2 and tell you that the result is 3.5. I can only work with whole numbers. And in fact, I'm just going to have to truncate the result. And so it works great if I want to do 6 divided by 2, but not if there's a remainder. So I'll have to handle this in some way. Also, what am I going to do if you try to divide by 0? I certainly don't have anything like exception handling in Lambda Calculus. So I'm going to handle this by saying that if you divide by 0, the answer is 0. Not right, but I'm handling it in some way. Now, if the number doesn't even go in one time, like what is 5 divided by 7? 7 doesn't go into 5 even one time. And so I'm just going to say the result is 0. Finally, if it can go in, what I'll say is that if it can go in at least once, then you've at least got 1 in your result. And then I'll ask, well, what happens if I divide m minus n? I took out one of them, and then I divide that by n. This is the part I want to do recursively. I'm going to keep taking n away from the number I start with for m and see how many times I can do this before I end up hitting one of these conditions, and I'll sort of bail out. And so that's going to allow me to do the division. Order n to the 4th to do division. And that's because the subtraction that we saw is already n cubed, and I'm going to do that n times. So here's what this looks like. Now, one thing I need here, I had this test right here. We haven't seen yet a way to determine if one number is less than another. And here's a function that can do that. And what I do is I swap these numbers around and I say, well, what is n minus m? And then I ask, is that 0? And then I have to negate that with the not function. And so basically what I'm doing is instead of asking is m less than n, I'll say, well, is n greater than m, or is it exactly 0? Because if it's one of those, I'll just take the not of that, and then I have it. And so with that in hand, I now have these pieces a, b, and c that I can implement. And so I say that the function that I want to pass into the y combinator is this one that has 3 pieces to it. So I get a function, and then I get the 2 numbers that I want to divide. And then I'll say, if the second number is 0, then I'm going to return this function that gives me 0. And notice these parts here where I'm just executing a function that I've selected. So if it's not that case, then I say, is it true that m is less than n? That means that n doesn't even go into m one time. And so then I'll return 0. But if it's not that, now I'm down to the c case, and I'll say, really the answer is the successor of this. If I subtract n away from m, and then I divide by n, just like this. And so you can imagine this being called many times until finally I end up with the result. And then I pass that into the y combinator, and then I now have a way to do division. There are many other interesting things you can do. You can represent linked list and get the first thing in a linked list. You can basically do things like in Lisp, where you have the car and the could'er functions. So this slide shows how to do that sort of thing. Now, at some point, you're going to want to test these things that you're implementing, and you want to jump from the Lambda Calculus world back into the world of your programming language. And so you're going to want functions like these. So how do I get a JavaScript Boolean from a Lambda Calculus Boolean? Well, if I have one of those true or false functions, then I can pass to it the actual JavaScript values for true and false. And similarly for a number, if I want to convert from a Lambda Calculus number to a JavaScript number, then I just need to add the value over and over again, and finally I'll get a JavaScript number. And so if I have those sort of functions, I can come over here to my terminal where I have implemented unit tests for every JavaScript function you saw in this talk, and I'm going to run all of them. And remember, these are highly inefficient functions, and so it's going to take a long time to run this. And so I hit return and it's done. How did it do that so fast? Well, one of the answers is that I'm running this in Bun, which is an incredibly fast JavaScript engine. It's way faster than Node and Dino. And so that's kind of cool. So you actually can do this pretty quickly despite the implementations not being very efficient. And so to wrap this up, clearly you don't need to know anything I said today. But it's still really cool that you can do all this in a world where all you have are functions, and you can impress all your programmer friends with this knowledge that you have now. You can find all my runnable code in this GitHub repository. If you want to run what I just did, you can just type in bun test. If you've got bun installed, then you can run that. You could also try running this in Node. I've got a Node version here, and what I found is that the Bun version was 5 times faster than the Node version. I've also implemented all of this in Python. You'll find the same code there. And in another repository, I implemented all of this in the Smalltalk programming language, really throwing back. So yeah, it might be interesting if you normally work in another language like Go or C# or Rust, to take a look at my JavaScript code and try to re-implement this in your favorite programming language. All right. I've got a bunch of resources here if you want to learn more about Lambda Calculus. And rate the sessions, and thank you very much for attending today.